So I think it's 11:30. Our coffee break is over. So it's time to start again, and we continue with some real work that they do at Concrefy, some real projects that they are involved in. I think Andrija will take over this part, and he is a well-known person to TU Delft. He did his PhD there several years ago, and then moved to Concrefy after that. So Andrija, floor is yours to tell us what you are doing there.
Thank you, Eric. Thank you for a brief introduction. Thank you also to Juan and Eric. They already said a few words about the Concrefy. So today is, let's see, November 13. Oh, it's a Friday, so Friday 13, not great for some start, but okay, we have to handle. So I would like first to introduce myself shortly. So my name is Andrija Blagojevic. I come from Serbia, and I am responsible for R&D department within Concrefy. It's a great pleasure today to share my experience and my thoughts with you. Especially because I also did a PhD, and almost 10 years ago I was more or less at the same career point where you are now. I guess most of you are in the first year of PhD, I believe, if I'm correct. Any response from the audience?
Yes.
How many of you are online at the moment?
They should all be there.
Okay.
Yeah.
Yes, at the moment I'm sitting in the front of my small laptop, and yeah, I see Eric on me, and I just share the screen in my presentation. Okay, so shortly about myself, I did a master's study at University Niš in Serbia. We also have 2 more people in the recent 5 days who come from Serbia as well, but from different university. Branko Šaviel, Mladena Lukovic, they come from Belgrade University. So I completed the master study in 2010. 3 years before I complete actually a master study, I did an internship in Spain. The name of the city is Gijón. This is how it is pronounced in Spanish. I speak a little bit Spanish, but it was long that time ago, so I forgot most of the words meanwhile, especially when I started to learn Dutch a bit. So it was in 2007, I was in north part of Spain, and I spent there 2 months, and it was first time in my life that I saw some, let's say, concrete durability issues and degradation mechanisms like corrosion in concrete, which is one of the most famous one, I believe. And I was triggered by that topic at that time. So a few years later, when I completed a master's study, I thought it would be a great idea to analyze a little bit more fundamental and more in detail the corrosion of reinforcement in concrete structures. So what I did, I moved in one even bigger port than Gijón. It was Rotterdam. As you probably know, Rotterdam is one of the biggest port in the world. Actually, I think only Shanghai is a bigger one. And close to Rotterdam, there was one small, nice city, Delft, 10 kilometers away, where in 2011 I started a PhD under the supervision of Professor Joost Walrafen. Here on the photo we can see some photos of my defense. So in a little bit less than 5 years I completed a PhD, and then another journey started 200 kilometers south from Delft in Venlo. I will just shortly share a few slides about the PhD work. Main goals of the PhD was actually to quantify the influence of cracks on the durability and surface life of reinforced concrete structures in relation to chloride-induced corrosion. I saw the schedule, so I believe you heard already in the previous 4 days a lot about fracture mechanics, cracks, transport mechanism in a concrete, so I will not go in many details. I will just briefly show some interesting results. After 1 year of a lot of literature study and state-of-the-art report, actually, the experimental setup has been developed. You can see maybe in this photo, I don't know, do you see my mouse, Eric? This photo right down at the bottom. At the end, 32 reinforced concrete beams have been casted, where I simulate a severe environment by putting containers at the top of the beams. And 3.5, yeah, we can see here, natrium chloride solution was used to simulate, as I said, aggressive environment, wetting drying cycles, 2 days ponding cycle, 5 days drying cycle. And what was the variables in the experiments? Actually, the crack width, the crack frequency, I mean number of cracks, also concrete cover and type of loading. Why type of loading is, for example, interesting in relation to self-healing is, yeah, when we have a variable load, which is quite often in reality and in practice, then the influence of self-healing is unfortunately a little bit less emphasized. But in case of sustained load and very small cracks here and there, I noticed the process of self-healing occurred and was very useful to slow down the corrosion progress. What was also very interesting, I measure locally corrosion, because we have a pitting corrosion, we can have a uniform corrosion. So by measuring a localized corrosion, after 2 years, we had plenty of results, and it was a really headache how to collect all of them and to make some kind of useful conclusion. And it was decided at the end to all beams, as you can see on the photos, it was beams were taken out from the setup. They were cut in thirds, in 3 pieces, each half a meter. Splitting test was carried out, and then we can see every beam from inside what happened there. And here we can see one very interesting conclusion. So at the moment, the thoughts in society are, yeah, there is no unique approach when we discuss about the influence of cracks on the durability. As you all know, there is a codes and limits which just limit the maximum allowable surface crack width, and there is a belief of some engineers that as long as the surface crack width is less than, let's say, 0.2 or 0.3 millimeter, then locally corrosion, it's just negligible and doesn't matter much. But as long as cracks are higher, there might be some problems. But what we saw in this research and what was very interesting to show, for example, here on the first photo, you can see the concrete cover of 20 millimeters. And this was actually very porous concrete, low quality concrete, which was picked up, of course, by purpose, because research cannot takes place. Let's say it cannot be very long. Just within 2 years, I had to complete the tests. So after 2 years of testing, we can see that unloaded beam, for example, we had chloride penetration, which reached the level of the steel reinforcement, and we have a slight corrosion. And this was treated as uncracked concrete, yeah. But what happened when we apply the load and when we have cracks? We can see on this photo between. So I will use a pointer. Just a second. Yeah, great. So this was one crack at the surface, and this was the other. And yeah, here you can see the reinforcement bar. Actually, we see that chloride penetration, if this is treated as uncracked part, you see this part here, there is no cracks, it's uncracked. We can see that the chloride penetration is, let's say, 140 millimeters. So comparable to this 30 millimeters, 140 millimeters. So what we can conclude here actually, that the surface crack width is not the most important parameter, but there is one parameter which is much more important, and this is the steel stress. So higher the steel stress, there will be the higher damage around the rebar, and surface crack is just a consequence of this steel stress. And this is a very nice showed maybe on this schematic here. This is so-called Goto cracks. Maybe some of you are familiar with Goto cracks. So we can see when we have, yeah, maybe I can show this in the pen. We had a 4-point bending, we had a steel stress, there were the cracks. So higher the steel stress, also the damage around the bar, and these internal cracks will be higher. In other words, effective concrete cover. This is effective concrete cover. So it's not this anymore. So probably chlorides penetrate here locally, corrosion started here, but then this is also very shortcut for the chloride. They can easily come here. They can also travel here, yeah, as you can see. And this is what we exactly see here. We see a lot of corrosion between the cracks, yeah, between the rebar and the concrete cover. So the main conclusion was what really matters is the steel stress, which determines the development of corrosion rather than the surface crack width as it is in the codes at the moment. Yeah, how to connect all the pieces at the end. As I said, we measured also locally development of corrosion, and what was very interesting is in every reinforced concrete beam, where was the point of maximum corrosion. Oh, somehow I lost my mouse. Where was the point of maximum corrosion rate? It was also the point of maximum steel stress in the beam, which confirmed our assumption at the beginning. It can be concluded at the end that, as I already shown, corrosion progress in a way is related very closely to maximum steel stress. And if we have a small cracks and some, let's say, lower value of maximum steel stress in a concrete, this damage can be acceptable. For example, here we can see explanatory model. So first of all, we have to distinguish two kinds of corrosion. Corrosion can be uniform corrosion, but on the other hand can be localized also. So in case of cracks, we are talking about localized corrosion as well. And higher the steel stress, which is, let's say, higher than 250 megapascal, can already shorten significantly the surface life of the concrete, reinforced concrete element. On the other hand, if you have a steel stress which is below 250, more or less we have a similar behavior as concrete is uncracked, let's say. But of course, this is all based on the certain concrete strength, and final conclusions of the thesis were actually that if we have a correct combination of maximum steel stress, appropriate concrete cover, appropriate concrete strength under certain environmental conditions, this is the way how we can design a longer life concrete structures. And also one very important stuff, what was this important fact, what was discovered during the research was that maximum load determines the damage in concrete in relation to corrosion. So it means once you have a damage on the bridge, imagine you have a small bridge, and once big track goes over the bridge, if this track makes some damage, after that, this damage what is already made there, it would be difficult to be recovered for chloride ingress, maybe with some self-healing new innovative techniques in the future. But in this work, it was proven that variable load, when we have a variable load, actually maximum load is the governing one. If you want to see more details about all this work, you can download the book from the internet. Yeah, this is the first page. So the PhD research was completed, and more or less this is what I just explained. I realized that we have to have optimum approach for the desired surface life. But somehow I realized, okay, all this stuff we did in the laboratory, it's valid under laboratory conditions. What would be the case in the real concrete? And as the title of my presentation says today, from labcrete to realcrete, I started to think more how we can in the future develop the system of concrete durability monitoring, which can be at the same time scientifically approved, but on the other hand also commercially also applied and user-friendly and very understandable for engineers on the site. On this slide we can see during the Defense Day my current boss, who just gave a presentation today, how we are discussing, and this is kind of the topics what we discussed then for the future: concrete durability, material health monitoring, structural health monitoring, energy efficiency. We share the same vision, and what was very interesting actually, how I came in Concrefy. At the same time, Tuan van Kasteren was searching for new people to build the R&D department and to focus on monitoring of the surface life. And on the other hand, I was very teased and triggered how I can still how I can shorten the gap between the fundamental research in terms of concrete durability and to find out some kind of pragmatic solutions, let's say, which can facilitate the decisions of asset owners. So I accepted this challenge. In a few days after the defense, I moved to Venlo, and I already started on Monday. And then we create one big project, asset management. But before I come to that topic, I would like to share this slide with you. So Tuan in the morning explained you how smart formwork works with a sensing system. So Doka is actually our mother company. 4 years ago, just in 2016, yeah, July 2016, they took over at that time BAS Research and Technology. So Concrefy is now, since 2 years ago, before the name was BAS Research and Technology, and Doka took over BAS, and they had a formwork they built in a way they do, and out of the blue with the concrete mode, they had a smart formwork, which in other words means that they can, let's say, increase the productivity on the construction site, and you saw benefits this morning, what the customers can gain and what kind of added value our clients can reach. But at the same time, I was thinking about concrete durability. Why should we be only involved in the construction phase of the project? Why don't we stay in during the whole, let's say, operational phase of the structure? In this way, we can help not only the contractor during the construction, but also the people who will be responsible for the maintenance and functionality and operation of this structure during the whole surface time. And this surface lifetime is sometimes 50 years, and in the future we will even design the structures which has a design surface lifetime of 100 years. And more or less this was the kind of portfolio of what we established then, that we as a company, we want to create decision support tools during the design phase, construction phase, operational phase. And the vision was from cradle to cradle. So we start here, we can see in the design phase, we use finite element modeling and simulations of young hardening concrete. This is how we can discover, for example, potential risks in the project. During the construction phase, you also saw Concremode as a powerful product, but we are also busy with process control and production control in the prefab on the site as well, also checking the quality of fresh concrete digitally. We are also developing a kind of sensors for that purpose. And asset management, yeah, asset management was a kind of a big picture. So this was the vision, but under umbrella of asset management, what we want to do actually is to provide real-time concrete durability monitoring system, which can facilitate the decision-making process of managers and experts. So this should be very user-friendly system with different kind of, let's say, levels of understanding. It should be, in the one hand, very user-friendly in terms of traffic light, red, orange, green, but on the other hand, has to be scientifically proven and validated that all knowledge, all guidelines, codes, and standards are somehow embedded in the background within interpretation technology and smart algorithms. You are still here, everybody?
Yes.
Can you hear me?
Yeah.
Okay. Do you might have some questions or remarks or any feedback till now?
Yes, I have.
I have a question.
Yes, please.
I do like more about your experiments, your thesis. Did you do some electrochemical measure in your specimens? Not only potential, the corrosion potential, but for example, electrochemical impedance?
Yes. So as far as non-destructive techniques is concerned, what was applied was half cell potential with two different kind of electrodes. One was embedded in concrete and the other one was external one. I also applied linear polarization resistance measurements. Mm-hmm. So I measured the corrosion rate, also, let's say, average corrosion rate of the steel rebar, as well as localized corrosion rate with another electrode and some commercial device. Mm-hmm. And I also did some resistivity measurements. So at the end, I have a bunch of results. Yeah, and if you download the thesis, you can see more details about that. Okay. You can always come back with an email to me if you want that we discuss some specific points. Like
okay. Okay, thank you.
I have a question.
Yes.
My thesis is about mitigating chloride and carbonation-induced corrosion. And I saw that during your PhD, you check both specimens in unloading and loaded specimens. I have a question about when you loaded the specimens, in the propagation of the corrosion, internal crack is control the situation or external cracks. I mean that when the rebar is corroded, it makes some cracks due to extended the voids, yeah? And it makes some cracks.
Actually, in my thesis, the focus, I didn't have the time to explain so many details. I just roughly touch upon the topic. When I'm speaking about cracks in this research, it was all about load-induced cracks. So before even chlorides were applied, I tried to simulate as much as possible reality. So in reality, we have structures where we have some loading and there is some cracks from early days. Yeah, this is inevitable. So cracks are inevitable in practice. So these kind of cracks are load-induced cracks. So 4-point bending was applied and cracks have been created. After that, I applied the chloride solution at the top. So we have to distinguish corrosion-induced cracks in uncracked concrete. This is what you are talking about at the moment, and load-induced cracks or deformation-induced cracks, which are there from the early beginning. And in that case, when we have a cracks, localized corrosion just starts in no time, within a few hours. But this is just locally, which I saw in the experiments. But how this further progress, this corrosion process, it was very interesting. And as I said, you can see the details. You can download the book and you can see the work there more in detail. If you might have any question, feel free to mail me.
Okay, thank you.
Yes. Any other question? Okay. So what I also learned during a PhD is have a big picture. This is what I learned from my supervisor, that whatever we do and whatever we focus on, in this case, my focus was on the influence of cracks on corrosion process, but big picture is very important. Yeah, the big picture in this case was surface life modeling. Sometimes it's quite challenging, and I believe for all of you is also challenging in this topic. Everybody has a certain framework, and everybody, especially at the beginning of PhD, this is what I did, will stay in his comfort zone, which is in a way determined by the topic. But whatever your topic is, whatever you do, always try to have a much bigger picture. This is just my tip. When we are talking about this bigger picture, my another bigger picture was how we can create a system that can measure concrete durability. 5 years ago, 4 or 5 years ago, it sounds like a mission impossible. But then together with people here in the company, we wrote a proposal and we got European Union support for one big project, which was Asset Management 2.0. And here you can see the logos of the parties who also supported financially the project. Ministerie van Economische Zaken en Klimaat in Netherlands, a couple of provinces, governmental party in Germany, and also as a main supporter was Interreg organization, Deutschland, Netherlands. I will show you now this project as an example, how we can come up from labcrete to realcrete. And let's say we will see kind of highlights of the projects, like goals, who were the partners, advisory board, and kind of deliverables, what we achieved at the end of the project. So project goals. The main project goal was, of course, smart asset management, but this is, as I said before, very, very broad topic. Our focus under umbrella of asset management actually is real-time concrete durability monitoring. So what was the kind of idea that we developed? The idea was that we developed the system. I call it a value engineering method or decision support tool, which is able to, which can enable asset owners, experts, managers, contractors to facilitate their decision-making process. So to help them. Sometimes some people, they just need a very simple answers like, okay, what I need to do. I'm not so interested in fundamental research and in the report of 200 pages. On the other hand, we have people who are experts and who would like to analyze many details. So we wanted to create a system and a kind of prerequisites. It was that system, it has to be a sensor which is completely wireless, that we can measure all projects all around the world from here, from Venlo. So all data needs to come up digitally via cloud system, and we have to create, let's say, smart algorithms and interpretation methodology, e-learning machine systems which can process these data. Those data has to go through official guidelines, codes, standards like Duracrit, FIB model code, and some pragmatic advice has to be given to customers before some damage occurs in concrete. So actually what we want to do, in other words, we want to warn the user before any corrosion even occur in the concrete that is going to come up within a few years. So he needs to do something preventively. So the motto of the project is better to prevent potential degradation in concrete and problems than to cure them afterwards. Project partners have been selected based on the requirements, what we needed. So we need a partner who is a specialist for wireless technology and power management. And this was a company, big company from Germany, Umlaut. They also changed the name actually. Since 2 years ago, they are Umlaut. Before the name was P3 Communications. And they have also offices worldwide, and they are very busy in high-tech industry, in automotive industry. By name says itself, P3 Communications. Before they are busy with communications and all these data management. We had on the board IBAC University and the group of Professor Raupach. Maybe some of you know Professor Raupach. He's a professor of the group of corrosion of materials. On the other hand, we had also representatives of authorities, let's say, which is the city of Mönchengladbach and Gemeente Venlo, which means in English municipality, Mönchengladbach and Venlo. Their role in the project actually was to come up with what kind of maintenance strategy they have at the moment and how they are dealing with the concrete infrastructure. What's the plan for the future? And what kind of issues and problems they have nowadays. We also have two small medium entrepreneurs. One of them was from the Dutch side, Van Deo Betonreparatie, is a small repair company, and one consulting company from Germany, IBB. And of course, Concrefy was a leader, took initiative and organized this project. Also had twice a year advisory board meetings with again people from university, from government, from institutes, but on the other hand also from authorities and some for example, Germany, BAST, very big institute for highway research. What was the innovative character of this project? First of all, we had to find a way how we can technology and engineering a little bit more relate with economical aspects. So how in the future, let's say, asset owner can really have a benefit from this system. It was obligatory to develop the kind of prototype which will be working. So it cannot be just kind of the scientific models in kind of a book in 200 pages with explanation, but it has to be something which really works in some pilot, let's say. What we applied in this project was really a multidisciplinary approach. So as you saw the list of the partners, there was experts for sensor technology, experts for material technology, but on the other hand, we have representatives of authority and people who maintain the concrete infrastructure. So I would say this, in a way, this was a transition from LabCrit to RealCrit. It was really applied research project. We had a certain time framework, 3.5 years, and goal has to be achieved. And what was also very interesting at the beginning, the first, let's say, the first 6 months we spent on a lot of inventarization. And one very important task was to analyze, okay, endangered concrete durability. How we can quantify in a little bit more pragmatic way what can negatively affect the concrete durability. As you know, we can have different weathering conditions. We have environmental classes. You can find that in the codes 206, where we distinguish the different classes. We can have, for example, concrete area which are exposed to carbonation, to de-icing salts. We have a marine environment, but on the other hand, we also have some concrete which is not exposed to these aggressive substances, and then it's more durable. Actually, we made kind of pyramidic approach. So we started from the top. Let's see what really affects concrete durability and how we can quantify that. In short, so we have 3 important fields. Concrete quality. When I say concrete quality, I mean if we have a dense concrete cover, the dense with a good quality, there is a higher chance that it's a better durability. If the cover depth is higher, also let's say the distance for aggressive substances to penetrate through the concrete also is longer, and it will take more time. So again, it's more durable. But also we have a lot of structural details which can affect these transport processes, like as I mentioned at the beginning of presentation, steel stress. We can have different kind of cracks. And at the end, we have to make appropriate balance between all these parameters and to come up with most optimized solution. But as you know, one thing is when we do calculation and design for something, and the other thing sometimes happen in reality. I mean, in other words, the spatial variability and the influence of many local effects can be very much significant. And then this is why we sometimes see a big scatter in reality from the things what we do in a lab and what the structure is designed for. I have one question for all of you now, if you are still there. And the question is, can you please tell me what kind of parameters can affect the quality of this concrete cover, and what kind of parameters in general, what you see in these 3 fields, can be of importance regarding the concrete damage and degradation, which can affect transport process, let's say. Any voluntary with at least one parameter?
I think the permeability of the cover will affect in terms of corrosion and the penetration of ions.
Yes, but if I believe some of you have already knowledge about the corrosion process, but if we start to count the list of parameters which can, let's say, endanger this structure, it can be, you already mentioned, like chlorides, permeability of the cover. Anything else? Somebody else would like to add some other parameters, which can be also mechanical parameters, chemical parameters, physical, whatsoever.
Diffusivity, maybe.
Correct.
And I think, for instance, water to cement ratio, as you mentioned, curing.
Yes.
Cover depths, the humidity of the environment, and in addition, like if we have any wet drying cycles and the concentration of CO2 or chloride.
All answers are correct. Anything else? What we missed so far? Eric gave a lectures about the cracks. So if you can have if you have a crack, the chlorides can penetrate within a minute sometimes, and reach the reinforcement. So in total, here I will mention just some parameters. The list is yeah, it can be much longer than this. I said the temperature. Why temperature? we saw today how much the let's say when we have a fresh concrete, we have a early age concrete compressive strain gain. And for example, if the temperature is too high during the hydration phase, as some of you already know, maybe we can have the problem later on with delayed ethnic formation. Moisture, very important parameter. Moisture, I always say, moisture is kind of a friend of a concrete during the hydration. As you know, that concrete hydrates, probably you had the lectures. We need a moisture, and if we have premature evaporation of moisture, it will negatively affect the development of many properties of concrete, strength first of all, then later on also durability. But later on, when we have a hardened concrete, in a way, moisture is an enemy. Why? Because if it penetrates from outside together with chlorides or for example, CO2 or any other mechanism, moisture is a parameter which is involved in most of them, and degradation of concrete will occur. Here we mention load because of cracks, so chloride ions, gases, abrasion, aggressive liquids. We can also have a sulfate attack. If we have alkali, we can have alkali-silica reaction. Some air voids in the cover can negatively also affect durability. There can be some dust during the execution phase of the project, fire. So as I said, list can be very, very long. So how to quantify this? How to develop a sensor which will measure all this kind of stuff is a kind of pragmatic-wise mission impossible. I mean, there is a kind of thousands of books which were written about all these topics. Yeah. So at the end, we decided what is the main parameter actually what affects durability is as one of your few first answers in a way is we call it concrete cover penetrability as a key performance indicator, which will govern the durability of concrete element. So idea was okay, if we are able to measure concrete cover penetrability, but wait a second, how are we going to measure concrete cover penetrability in real structures? Which parameters we need to measure? How? Do we need all different kind of commercial sensors what are on the market nowadays? There is some sensors which measure chloride, okay, but it's not a perfect sensor. It can survive a few years in concrete. And it needs to be recalibrated again and again. And there is a sensor for pH measurements, and there is a different kind of non-destructive measurements. And all these results are just number. If there is no good interpretation, it's a challenge again and can be misinterpretation. So all these kind of issues, how we solve it, we said, okay, we are going to define key performance indicator, and we are going to focus on the most important parameter to be measured. And later on, we will relate this parameter with all degradation mechanisms as they are described at the moment in DuraCrit, in guidelines, in FIB model code, and other standards. So you can see in this table, and probably I see you already had a lecture. Branko Šavija gave a lecture about modeling of and the transport durability. And probably I shortly had a time to see his presentation, but he probably mentioned that water ingress in a way is that the water is a parameter which is involved in all degradation mechanisms. For example, if we have in a reality, if you look reality, if we have a dry concrete, chlorides cannot penetrate in a concrete if there is no moisture. Most of the time when we have de-icing salts, which are used during the winter, there is ice, we put the salts to melt ice, and then together with water, ice became water, chlorides penetrate through the concrete cover. And once they reach the reinforcement, corrosion will start. Alkali-silica reaction. How many of you know what is alkali silica reaction? Some of you? Did you hear ever for alkali silica reaction? It's a kind of degradation in concrete also. So we have alkaline binder and silica in aggregates, and when they react with the presence of water, there is a gel, and this gel will expand, which will make a pressure in the concrete cover. So in other words, concrete cover will become more permeable. Frost attack, for example. So we can if water is present in the concrete cover, and during the freezing time, when the temperature is below 0, we can have ice, and it will affect negatively the penetrability of cover again. So we decided to develop a sensor. You can see here the sensor. An idea was that this sensor is a wireless sensor and that we can measure the moisture ingress in concrete. Actually, what we actually measure first is electrical resistance. By measuring electrical resistance and by doing a calibration test in the laboratory, by creating isotherms, we are able actually to relate electrical resistance and moisture content. And by doing that, we are able to measure at any point in time every centimeter. As you can see here, the sensor is 50 millimeter is the depth of the sensor, so we can create the profile. We have 3 different levels of measurements. Measurements are done between the rings, and if this sensor, this is the concrete which I showed you in the previous slide. This is the concrete cover. So if the sensor is embedded in the concrete cover, it looks like this. So imagine this transport diffusion process of moisture sometimes takes a lot of years. We are able to measure what really happens in real structure. So it's not assumption anymore. It's not something what is based on the measurements in the lab only, but we have a sensor in a real structure which give us real-time information, which is very valuable for further prediction and predictive analytics. Let's say we can know, are we in a green zone now that everything is okay, or the problem is going to come within a few years, or imagine that some unpredictably happen because of any reason. So sensor will be able to capture this moment like today and send a signal via web portal and internet to the client. It will send a notification. This structure at this element, red zone, something is happening like now. So you have to react upon that, and this is proactive approach. As you know, most of the people who inspect the concrete infrastructure, they see, let's say, outside part of the concrete, skin of the concrete. So most of the time we have to wait for the problem that it happened inside of the concrete. As you know, for example, corrosion will start inside of the concrete and it will not be visible for many years. And once we see the consequences and signs of corrosion at the top surface of the concrete, we know, okay, there is a corrosion, there are the problems, we have to repair it, but then we realize sometimes that there is too much spots to be repaired and the whole structure is endangered. And one of our partner, Gemeente Venlo, showed one great example. It was a parking garage. I don't have in this presentation this photo, but I will shortly explain you that. There was a parking garage and there was a corrosion there. And once they found out that there is too much corrosion, they put a coating, but it was already too late. And after a couple of years, they decided to demolish whole structures and to build a new one. So it cost them a lot of money. And imagine that they have this kind of sensor system, then they would be able to capture, I call it early warning signal. So this is kind of early warning mechanism, which tells you before you are in a problem that you are going to be in a problem and you can react upon that. So in this case of Gemeente Venlo, it would be possible many years in advance to find out that this is going to happen, and then we can, we would be able to do some preventive actions, and this garage will be still there. Before I start to explain you how we started tests and what we did in the lab and how we correlate really lab crit to real crit, is there any question maybe? Is it everything clear so far?
Hi, Andrija. I think you have one question in the live event Q&A panel. Can you see that?
Unfortunately, I cannot see. I just see the screen with my presentation at the moment and the guy who is speaking at the moment. For example, Sean, I see you now. So maybe Eric.
Read it, Sean?
Salam asked, were your specimen under sustained loads? If so, could you please explain how did you manage to keep constant loading, taking into account the creep and relaxation loss of the load?
So probably this question is really in relation to PhD research?
It was asked half an hour ago, so maybe related to your last part of the presentation.
Okay.
Yeah, that's one.
I will. If you see the book again, actually it was not a sustained load, but a load was applied. It was a kind of load was applied to create a certain crack width at the surface, and once it was achieved, it was not changed anymore. So it means there was an effect of relaxation and the creep. So in time, load became actually a little bit lower. Yeah, you can find this calculation and analysis in the thesis, and this is why some cracks they became little bit lower in time. Is it answer clear? So it was not a sustained load all the time. If you have a sustained load, the same load all the time, then the crack will become even higher in time. But in this case, there was a chapter about that whole chapter about creep and the relaxation and shrinkage calculation in the test setup. Okay, we go further with the presentation. Let me see. Yeah, so what we did in laboratory before we designed a wireless sensor, which you can see in my hand now. I think you can see it. In order not to lose the time at all, we first decided to go with a wired version of the sensor. So you can see here in the photo many of examples with the sensor inside of them. And this wired sensor was actually applied in a concrete cubes, 15 by 15 by 15, in a different conditions. So as you can see here, we have a climate chamber where we have a lot of samples, and more than 90% is RH, 20% temperature. Lab conditions where we have RH between 30 and 50, and we have outside conditions where we have reality. Yeah, reality means sometimes RH is high, sometimes it's low, sometimes it's sunny, sometimes it's rainy. And all these samples actually are wired samples are connected to the system. We have one extended database where we collect all the data. The measurement started 3 years ago, and our plan is not to stop with this kind of measurements at all. So whole future, the measurements will be just running more and more. And time, I say time is working for us. So as you know, durability is long-term process. In other words, if we have a results within 5-10 years, it will be always more valuable than some results within let's say less than a year. We also have some specimens which are casted 8 years ago, but I will say more about that later on. Some big walls. At the end of the project, we developed these two sensors, let's say. One is for the new concrete. So maybe I didn't say that. So this solution is valid for both structures, for the new structures as well as existing structures. And we will see later on how the procedure of installation works in the existing structures. But you can see for the existing structure, we have a small notch here and there, which is 2.5 millimeter, and this is the sensor for the new structure. This is the cross section of the sensor that you can see how it looks like. And why the sensor is so big is, of course, that we need a lot of electronics to be inside, and which will make possible that the sensor is wireless. There was actually a big challenge. The idea was that the sensor, once we embed a sensor in the concrete, it has to survive at least 50 years. So we need without human intervention at all. Because our vision for the future is once we install these sensors, that we can control whole infrastructure worldwide. And the idea is not that every now and then somebody goes and change some batteries and again and again. So the wireless system and power management were developed in a way that the battery in the sensor can survive for many, many years. Don't ask me how it was possible, but at the end it was possible. It was the biggest challenge at the beginning. And we use actually LoRa technology system. It means if we have one big project and there is sensors in the project, let's say 20, 30, 40 sensors, there is one big gateway which will collect whole data from the sensor, send them to the cloud, and then we download the data directly from the cloud, and all this data go via smart algorithms and interpretation methodology. The sensor is also, I will show you here, I don't know, do you see on the camera, but the sensor is so flexible that it's possible to open a cap and imagine in 10 years from now there is a new technology on the market. You can just take it out, this electronics from the sensor, put a new electronics, a new technology system inside, plug and play, and it will work again. So now, for example, this 5G is coming, maybe in 5 years there will be kind of 6G, 7G, who knows, huh? But any technology comes on the market, the sensor is flexible, that it's possible to, as Tuan said in the morning, adjust, adopt, adjust, and improve. Sensor is embedded in the cover, as I said before. What we measure exactly with the sensor actually is the temperature of concrete and resistance. And we saw this morning how it's beautiful. With the concrete mode, we measure the concrete temperature and outside the temperature. And by measuring these two parameters, we saw at the end how we came up with very important and emphasized added value for the customers. We saw the examples how customer can save huge amount of the budget in the projects by shortening the cycle times and by shortening the completion time of the project, by knowing which kind of mixture he needs under which circumstances. And as Tuan said, the vision is in the future that we develop the system that we can have a control of the concrete infrastructure whole surface life. So until the phase of when we need to demolish the structure and to reuse the concrete again. What I just said, actually, we can see in this slide. For example, this is the Zeelandbrug in the Netherlands, one of the biggest bridge. And you can read on internet, they have many of issues, challenges, and problems nowadays. So then you can imagine you have to close the bridge, you have to stop the traffic, you have to inspect it, you need a lot of equipment, a lot of people. In other words, it's time consuming and it takes time and manpower and inspections. And our vision, especially for these large-scale projects, to have this kind of real-time concrete durability monitoring system, where sensors just can inform us and send us a notification, hey, there is a problem in this bridge at this column. So we know exactly the moment in the time when we need to react. So then we go there, we do some, not we, I mean, if the customer is from Australia, he can call local consultancy agency to do some extra check just in that structure at that position, even though there is no any significant damage which is visible at the surface of concrete. So damage is just about to come around the reinforcement, let's say. Chlorides are just about to reach the critical chloride content at the level of reinforcement. So one of the strategic goals in the company is visualization. Everything what we do, we try for the clients to visualize. Maybe if I show you a lot of texts in a few days from now, you will forget 90% of the stuff which I presented. But this event is recorded, so you can always come back. But in general, but if we present the things in visualized way, it's always more user-friendly, and the people in the real Crete, it's easier for communication with them. It's much more clear, let's say. They're not so much interested, sometimes managers, at all in the details of carbonation, of chloride-induced corrosion, of any other degradation mechanisms. They just want to know what they need to do and when, and how much they need to invest for that. So what we do, the sensor measures the data, we measure the resistance, and by having a calibration test, we know what's the moisture content, we know the profile, and we know the progress of moisture ingress within the concrete cover. And by knowing this and by applying a different kind of guidelines, what we have and codes, as I said, we are able to create kind of assessment of all these different modules, all these degradation mechanisms. And what we developed is a chloride ingress model, not a model, but module, let's say. We use existing models in a way. What we do with the sensor, for these existing models, we provide more, let's say, realistic input in these models, because in these models there is too much empirical parameters which affects the final result. But if you have a sensor and if you have a real-time data from real project, your results will be more accurate because these inputs will be more reliable. It's so simple it is. So here we can see we have a module for delay deterioration formation for the cracks. So if there is any crack around the sensor will recognize it also. Freestone model and carbonation as well. Probably you see this kind of graph before. This is the level of deterioration, and during the initiation phase, yeah, it can take a lot of years that chlorides, for example, penetrates and the corrosion starts. But we don't see this process. This is why we believe it's great to have a sensor in a concrete cover. Then we can monitor this development of the moisture penetration. And before we even have a stage 1, we know that it's going to come in few years or in few weeks or in 20 years from now. And why this is important actually is important for managers to create budget optimization, to create predictive maintenance strategies. So they want to know when they need to invest money and when they can just save money. Is it better to do a small preventive interventions per year, or just to do one big intervention in 5 years? It always depends, of course, on the budget of the clients and their goals. Yeah, here I will show you just few details of those kind of models. This is, for example, chloride ingress model based on Duracrit. And what we can see here, this is idealized curve, what is given by the guideline. But what we really measure with the sensor exactly in, let's say, that concrete, it's something like this. Huh? So this is the reality, these dots, what you see. So sometimes it fits the curve, but sometimes it does not fit the curve because of any reason. And when it's like this, we can always receive the signal, and we know that it's not like we planned to be. Probability of corrosion. So in the portal, we are able then to assess what's the probability of corrosion in terms of, yeah, is it 5%, 10%, 50%? And the limit state adopted here is by Professor Angst in Switzerland University. So he created in one publication, you can read about that, log normal distribution, and critical chloride content actually is modeled as a stochastic variable. So in the literature you can found out that there is many different values, but this one is much more realistic. I believe myself as well. That yeah, the critical chloride content depends on so many parameters. It cannot be universal value, and this curve is much more realistic, let's say. So how to come up to very simplified solution for the customer, for example, who does not have any knowledge about concrete durability, about concrete at all, let's say. So they would like to have kind of traffic lights. So we are here to provide this kind of traffic lights system and user-friendly solutions for them. Here we can see the graph of Matthews, who gave a contribution to FIB model code. And we can see, for example, what is the negligible rate, what is the low to moderate or high rate of the probability of corrosion. But again, based on the circumstances and local effects in some real structure, for example, if you have let's say 0.5% of ion concentration, you can have a chance of only 5% that corrosion is going to happen. But at the same time, this value can be also much higher, what you can see here in the graph. But at the end, this is the mean value, yeah? So this is the mean value. This is kind of what we expect, what is the idealized curve. But what can happen in reality can much deviate from this also. And this is why we need a sensor, and this is why we need to measure what really happens in concrete. One more example of carbonation model, for example. So based on the calibration and based on the accelerated carbonation tests in the laboratory for specific mix design, and the measurements on the real time. What does it mean real time? In real time, we measure what is really, for example, relative humidity. So if relative humidity is between certain level, we can expect the carbonation progress. But if relative humidity is too low or too high, there is no much progress of CO2 in the concrete cover. So again, from a lot of complexity, we come up to the client with the colors, and you can see here, for example, this is kind of limit states for some clients that if it's between, if hypothetically, let's say if it 50 millimeter is the concrete cover, if it's up to 15 millimeter, it's still in a green zone, and it means that the remaining surface life is still very, very long. But as we discussed, if something unpredictably happened, the sensor tomorrow will already change the status. And if you have a case that the CO2 almost reached the level of the bar, we can have a red light, which will mean this was just one of the example. We see that in less than 5 years, the carbonation induced corrosion will start. And you can react upon that. So you can apply some preventive measures. And this is very important for asset owners. Why? Because they can save a lot of money. So it's better to invest a small budget into small interventions before some severe damage and severe problems comes in a few years from that moment. Then it will cost much more. The same is with a car. You have a car, you go for regular check. You change a lot of things per year. But if you don't do anything, if you just ride your car, yeah, for a few years you will be fine. But then out of the blue, your engine will be dead, and then it will cost you 5 times more than expected. This is kind of schematic representation, for example, for carbonation, how it works. Crack detection model. So if there is any crack in surrounding of the sensor, it will be also recognized. And here we can see, for example, if we have a healthy sample without a crack is the orange line. No, sorry, yeah, we call it average resistivity. So it was the healthy sample, and then when the crack appeared, what happened? This is the resistivity out of the blue jumped very high. It means it's a dry crack. But once at the same crack there is a moisture is coming, the value will go completely down when it's wet. So in a way, this was the healthy sample, this was the dry crack, this was the wet crack. A lot of validation have been done also for many assumptions, and this is what Portal shows, for example, for uncracked sample. Yeah, we see all green and sometimes yellow, but this is instantaneous value, it's not cumulative. And when we have a cracked sample, we see emphasized red dots. Some example of freeze-thaw model. Yeah, as you know, if the temperature has to be lower than 0, it's one condition, and the other condition is for freeze-thaw attack is degree of saturation. If degree of saturation is above certain limit, there is a threat in relation to damage, and if it's lower, then it's not a big threat. Then, of course, there is the influence of so many parameters. For example, type of binder. Here on the graph right, we can see what happened in. We did some tests in a lab also with SEM1 when you use SEM1 and when you use SEM3B, and all other parameters actually are the same in these two mixes. We see that the resistivity of when this transition happened, when water became ice, resistance is higher in case of course, blast furnace like SEM3B than in case of SEM1. This is example of delayed heterogenic formation model. So if the temperature in fresh concrete is above 70 degrees from any reason during the hydration, there will be a red light saying to the client, we will not wait even that it's 70, even if it's a 60, there will be like a message and notification to the client. Okay, your temperature in concrete is 60, if it reaches 70, it's already a big problem. And then we call this digital consultancy. This is also one of the strategic goals in the company, digital consultancy. We try to warn the clients and to help them by having our 24/7 support from Concrete Competence Centrum here in Venlo and sending them digital advices what needs to be done before they are in some bigger problem, let's say. And this is one example with delayed heterogenic formation. Installation in the existing structures. So in the new structure, this is the right sensor is in the new structure. In the existing structure, we need a coupling mortar. Coupling effect of mortar concrete then is very important. So how does it work in an existing structure? Also the inspection procedure, we drill the core, we analyze the core, and with a special mortar, what was designed for this purpose, actually via this mortar, we measure what happens in existing concrete. Some correlation factors have been developed and many tests have been done here in the company. We will see some photos later on, an analysis. This is some of the tests to see how the existing concrete actually and the moisture ingress in existing concrete, how it's measured by sensor via mortar. And some correlation factors have been developed. And this is, as I said, these beams are casted like 3 years ago. One sensor is installed, as you see on the photo, we call it cast in situ sensor in a new concrete. The other sensor was installed after a couple of months. But here in the middle of the beam, we plan in a few years to install another sensor and then another, just to see this aging effect of concrete on the results. Before I go to one pilot project where we install the sensor in the bridge, there might be some questions maybe, or remarks or any feedback. Yes.
What is the criteria to decide how much sensors do we need and where the sensors we should implement in certain elements? So for big structures like the bridge, So where do you locate your sensor in some certain columns? What is the criteria to decide that how much sensors do we need, or what is the optimum places to implement the sensors?
Thank you. Very nice question. Actually, we have here in the company a lot of experience regarding forensic engineering, inspections, damage. So we have a grip on what happens in existing infrastructures nowadays. And based on the, how big is the structure, let's say we always have to, together with the client, come up with optimal solution. Let's say, he cannot install thousands of these sensors because it will cost a lot of money. But we are trying, let's say, idea for the future and for the business development is with as less as possible number of sensors, again, to have a good insight and good feeling about what happened in the structure. Every structure is another story, so it will be carefully analyzed. What are, let's say, what are the points in the structure which are most vulnerable and which will be most vulnerable to, let's say, corrosion of any degradation mechanism, where we can expect the damage. And at the same time, some sensors, of course, are installed as a reference in some places where we do not expect any damage, and we have some reference as well. So at the end, you have a good feeling about the structure. The same is now when you go to inspect some structure. For example, me myself, I was 4 years ago in a big tunnel in the Netherlands, and it was a tunnel which is the length of the tunnel more than 1 kilometer, and there was a big renovation project, and the whole tunnel needs to be renovated. And then I just finished a PhD, and I came up with this mindset, and then I thought, okay, I will need a few years to inspect this this tunnel probably. But then I had a few weeks time, not years but weeks. I said in a few weeks to do all job. Oh my God. So in other words, you have to decide how many cores will you drill in this tunnel, at which positions. You cannot drill now thousands of cores. We drilled around 12 cores. So from these 12 cores, we decided where to drill it and why, of course. So carefully strategy was developed. And for the future, every project, I would say, has to be discussed and based on the budget of the client and what we think is the most optimum solution will be analyzed and suggestion will be given.
Thank you.
You're welcome. Any other question? Okay, I think we will be done in around 15-20 minutes from now. So I will show you now the most interesting part. What was the pilot project? In Mönchengladbach, actually, there was one bridge, the small bridge, which was deteriorated so much and so severe that they decided to demolish it and to build a new one. This is some photos during the construction phase of the new bridge. The things which I haven't mentioned yet maybe is that sensor is so smart that when it's in the formwork and when the concrete comes to the formwork, sensor recognizes that concrete is there, and it gives the signal also to people, let's say, who are in charge of the project. You can see on your mobile phone or via internet on the portal that concrete is just poured, and then you can see the development of the let's say fresh concrete. This is more or less what you saw this morning with the concrete mode. How does it work? But as Tuan also said, the purpose of this sensor is to stay in the concrete more than 50 years and to have in a control, for example, this bridge for more than 50 years. Let's see how does it look like visualized. So this is exactly that bridge. In this bridge we installed 16 of these sensors, and still measurements are running. We receive the data on a daily basis. Once you are in a Concrefy, I will show you on the portal how does it look like. For this purpose, I downloaded a couple of of photos in this presentation, which you will see later on. But in general, what happens? So we have a bridge, we have a sensor. The sensor is embedded in the concrete cover. The sensor measures the data, sends to the cloud. In the cloud, there are a lot of algorithms based on guidelines and standards. And for all of these degradation models, limit state have been defined. And as an output, we have a traffic light and also recommendations what needs to be done. This is one of the examples for the pilot project. This is the walls built in Venlo 8 years ago as a part of another Interreg project. So in existing structure and the strategy for existing structures, you can see here. So we use a radar, we do a scanning, we drill a core, we bring a core in the lab, analyze it, and then we put a sensor with this mortar, and at the top we have some Sika flags. And then within the 3 months we have a moisture balance between the mortar and existing concrete. And after 3 months, all data are actually what we measure with the sensor, are performance of existing concrete. This is from our web portal, decision support tool. So we can see the different kind of projects, and idea of this asset management project is also that anytime you can on the map click on any project and you have kind of, I call this birth certificate of concrete infrastructure. So anytime you want to know anything about any project, with few clicks, you can see what was the binder type, what was the water cement ratio, when it was casted, what was the history, what kind of interventions have been done meanwhile. Yeah, this is what I just said. You can see all these details and performance. This is the performance per sensor. For example, this is from pilot project in Mönchengladbach. So if you are a manager, you are only interested in these slides. If it's in the company, there is a durability expert. He will be digging more into depth, like, okay, what was why you pick up this limit state, how, what does it mean? Somebody wants to see the raw data maybe. So we have explanation for, let's say, different levels from managers, for managers, budget holders, experts, durability experts. This is the raw data, for example, resistance, resistivity, degree of saturation. What is the real-time chloride diffusion coefficient? All in all, at the end, it can be concluded. So final goal is to maximize the asset value. And how we can do this? By providing this real-time concrete durability performance. It's a platform, so it's not a sensor. It's a whole system. I call it value engineering method. We have to find appropriate balance between performance, risks, costs, availability of infrastructure, maintainability, reliability. We want to help asset owner to make his decision when to spend the money and when to save the money. He can do this only by carrying out life cycle management costs at every moment, what we can actually do for him. And again, he will have a digital portfolio of solutions, and based on his wishes, he can decide what is the best for him. By doing this, as I already said, we increase the safety, reliability, and availability of our concrete infrastructure. This is kind of big data analytics for concrete durability performance. And the idea is also that we create in the future digital twin data information management system. So every maintenance and forensic engineering which have been done in the construction industry that in digitized way can be downloaded any time via web portal, just within a few seconds. We call this digital dashboard. And then I have one question for all of you, if you are still here. The next step for the future is how can we measure and quantify the effectiveness of self-healing in concrete remotely? This is the question what you can think about that, and we can discuss in the future. Yes. more or less that's all for today. I was a little bit, it took me a little bit more time than I planned. But
well,
okay.
thank you, Andrija. I think that was a very nice overview of your PhD and also what you do now. So that's very good to see that how you can make a future also after a PhD. Yeah? So that's
Yes, this is why I took a little bit more time to explain also that I was in the same shoes as other researchers 9-10 years ago. And then I stayed in the same field and the same topic, but now I just do more things which are, let's say, more related to the real crit. But the best combination is to be at the both sides, you know, to shorten the gap and to make a bridge between fundamental research and the commercial things. So then you are in the field of kind of applied research, and I really enjoyed. Concrefy is also multicultural. We had students from TU Eindhoven, TU Twente, TU Delft, who are internationals as well. Some of them go back and forth to TU Delft as well, who used to work in this project as well. Yeah, who gave a great contribution to the project actually.
Okay.
Yeah, but it's nice environment. It's international, and yeah, once you have a time, all the students who are part of these smart things, we are glad to host you and to give you also a lab tour and to show you some other stuff.
Okay, now there's some final questions for Andrija. Burning questions.
And the final message, as I said, always have a big picture, make a small step and try to upscale it. So in this project asset management, actually, we took a lot of effort to develop this prototype. We started with one small pilot project, and idea is that in a few years we upscale this internationally.
Yeah. Okay.
So I believe the same we can do with the self-healing, but as a first step is how we can measure the effectiveness of self-healing in concrete remotely.
Yeah, that's true. That should be solved, and yeah, Gabriel is the one that should solve that because he is working on the sensing. So he should come up with a good idea to do that. Well, thank you very much, Andrija.
It was my pleasure. I don't know
wonderful visit to Concrefy.
Is the PhD students expected more or less something like this today? But as I said, I try to present the transition from fundamental research to some pragmatic solution and digitization, productivity in the future of concrete infrastructure.
Yeah, I think this was perfect. So, well, this with this session, we end actually our Smartings training school for the online attendees. So for them, it's finished. So you can start already your weekend. But the people from in the Smartings project will also continue this afternoon. First to work on the project that you have gotten. So to repair our swimming pool in Portugal, and then you have time for that until 3:30. So then we will be back in another team session to listen to your presentations, and then from 5 o'clock we will start our pop quiz that we are still preparing, but it's almost done. And then from 6 to 7 you have to prepare dinner. That's the idea. And from 7 we will start the dinner. And we'll see how that goes. So I'm looking forward to that. So yeah, that's it for now. Lunchtime, and then see you at 4:30 in the team session. Bye.
Thanks. Ciao.
Thanks, Andrija.
Thank you.
Thank you.